But I would like to introduce our next speaker, Matti. He is an associate professor at Aalto University, Finland. Areas of expertise include architectural, climate change, circular economy, energy efficiency, and carbon footprint. And he'll be talking about carbon footprint calculations this morning. So let's hear it for Matti.
All right, tere hommikust. Good morning, everybody. For some reason, your conference organizer has chosen, after a fun night, you to hear about climate change. I don't know how this balances your feelings, but anyway, this is what's on the menu next. As said, I'm a professor at Aalto University. My background is in architecture, and I have actually designed one or two long buildings, but that's a long time ago, and I'd love to do more of them one day. So this morning I'll be talking about carbon footprint and some of the calculations. It's not going to be very theoretical, it's not going to be very academic, but slightly so. I would like to discuss that. Why is the carbon footprint something that's so much word of the day in the building sector nowadays, and then again, how to calculate it, and how could you take that into your daily business or daily routine? So these would be the sort of like the takeaways from today's presentation. But let's start from the atmosphere. Nowadays, the atmospheric content of carbon dioxide is around 420 parts per million. That's parts per million. That's a super small fraction. However, this very small dose of CO2 in the atmosphere has rather dramatic impacts to our planet. And actually, we can go and look at Earth's history from geological records, and we can see that what sort of conditions has there been on the atmosphere and on our planet in the past. And the last time we have seen the atmospheric CO2 figures, it was around 4 million years ago. And as we all know, CO2 is like a warm blanket over our planet. It warms our planet, and that causes, of course, the glaciers and ice sheets to melt. So 4 million years ago, when we had similar amounts of CO2 in the atmosphere, the global warming potential that it caused, of course, caused the sea levels to rise. And we can see from the records that the sea levels were from 5 to 25 meters higher than they are nowadays. In other words, if we don't take carbon out from the atmosphere, if we are just happy with carbon neutrality, that okay, let's stabilize emissions to their current level, the planetary response will be like this, from 5 to 25 meters of more sea level. And nobody wants to have that, of course. That wouldn't be, of course, the end of human race, nowhere close to that, but it would be a dramatic shift in our socio-economical structures. So therefore we need to do something about CO2, and the good thing is that behind me we have a large storage of CO2 in the form of carbon in wood construction, and that's why it's so relevant for us who are working with wood and for the built environment to know the basics of why is it important and how to take that into account in our businesses. So for these reasons, the International Panel on Climate Change, the IPCC, has said that by mid-century we should cut emissions from the building sector by 80 or 90%. So that would be an immense reduction of emissions. This would be needed in order that we would avoid a very expensive and dramatic and even catastrophic climate change. That would then, of course, have to do with the sea levels. So, in order to do so, there are a set of policies nowadays in place. Here is the timeline or the evolutionary line of these policies. In many countries, we already have regulation that sets minimum requirements for energy efficiency of buildings. Here in the European Union, we have had this for over a decade, and this has done a good job. But at the moment, it doesn't seem to be sufficient means to combat climate change. So then the next step would be to start estimating that what are the whole life carbon emissions associated to a building or infrastructure works. Thereafter, it seems, or in the forthcoming European regulation, there are going to be limits to carbon footprint of buildings. I will talk about that towards the end of my presentation. But ultimately, I argue that even that's not sufficient, and we should actively start removing carbon from the atmosphere and store that somewhere where it's safe, where it stays for a long time, and the built environment is a perfect place for that. So, how do we use our natural resources today? 50% of all the raw materials that we extract annually are used in construction. And the trends are going upwards, so we are consuming more. There is the growth of population that leads to more buildings being built. Then we have the aging infrastructure that needs to be repaired, and then ultimately the sea level rise, which has already caused some of the wealthy cities that are there by the seashore to build storm walls or flood walls towards the sea. So all these factors are accelerating the use of construction materials. This is the remaining carbon budget if we wanted to contain global warming below 1.5 degrees. And as a side note, I should say that it already appears like a mission impossible to keep it below 1.5 degrees. But let's have that as a reference value. And to this value, I'd like to compare that what are the known emissions that are associated to the production of cement, steel, aluminum and plastics with current technologies and current demand trends this century. So if we kept on making these 4 products with known ways of measuring, manufacturing them, the associated emissions would be over 900 gigatons. So we can see that these 2 figures really do not match. And now we are talking only about the production of these 4 materials that are mostly used in construction. So obviously something has to be done. And if we could make our factories run on very, very clean energy and do that on a very energy efficient manner, we can push this figure down towards 500 gigatons, which is still around 2 times as much as the entire global remaining carbon budget. And researchers have said that theoretically, with very radical interventions of circular economy, these figures could be pushed down to say 300 gigatons, which is still above the global entire carbon budget. So maybe this underlines the relevance and importance of the construction sector. Of course, these are rather depressing figures, they don't make anybody smile, but on the other hand, we can look at these figures from the viewpoint that in every construction project, with wise choice of materials, we can do so much good for our planet. And that's not rocket science, that's something that can start today. Alright, so let's get back to the quest set by the IPCC. We should cut down emissions 80 or 90%. However, there is one complication, namely that due to growing population, we need to build more. During our century, we are about to have 2 billion new homes, because cute little babies are born every day. And with a very good and justified cause, people who are living in developing countries in poverty want to build their way out of poverty and maybe have 2 rooms, one for their 5 kids and one for the parents and the granny and whatever your maybe side business is that you are doing at home. So it's more than understandable. But this leads to an acceleration in the use of construction materials. So, what is the wise way of choosing construction materials then? What are the differences between functionally similar building products? This might be the first question that we are led to think when we are looking at these figures, but actually I would argue that this is not the right question. The right question is to look at these things on a building level. What are the differences in emissions and environmental impacts of functionally similar buildings? Because buildings are made of, a vast array of different products. And even these nice log buildings, if you want to have electricity and water in them, you need to have so much plastics and metals. And if you want to, build them somewhere else than on this flat factory floor, you need to excavate soil and you need to bring some gravel or do some foundations, probably with concrete. And you need to have roofing and so forth. So there are lots of materials that are associated to the building regardless of its frame material. And the thing is that even in a fully wooden building, we have also other materials than wood. And these other materials might cause collateral environmental damage that we didn't intend when we chose wood to be our frame material or facade material or cladding material. And therefore, it would be interesting to see that how can we decouple the use of sustainable and non-sustainable materials from each other? How can we simplify buildings? Or how can we make our living and building habits maybe more robust and more simplified so that we don't need to have this complexity of different layers and different materials performing for different functions in the building. Of course, this also has to do with the change of building policies, which isn't a fast track. But nevertheless, it's inevitable that also has to play along. So, life cycle assessment is the thing that will help us in figuring out that how much good sustainable materials can do in a building and how much bad good unsustainable materials cause to our nice building, be it of log or recycled bricks or round earth or any other material that we can conclude that is sustainable. So simply, in life cycle assessment, we are just summing up the environmental impacts that arise first from the production of materials, then from their logistics to the site and from the site activities, then from the use and repair in the building, and then from the end of life. Let me try to explain this in a very brief way. So when we are looking at the production of materials, we should take into account everything that happens at the source where we extract the raw materials. When you go to the forest with your harvester and cut down a tree and take it to this nice mill and craft that into a beautiful log, all energy that's associated to this is causing emissions, and these would have to be taken into account. Now the benefit, of course, if I have understood correctly, that you are doing here in this beautiful part of Estonia, these buildings mostly by hand, that's of course a great asset compared to a fully automized industrial facility, unless that facility would be running on clean energy. Anyway, production of materials is the thing that is nowadays raising its importance, and it's becoming even the heaviest when we talk about climate impacts of construction compared to all the other life cycle stages. Alright, after we have our beautiful products manufactured, then we are transporting them to the site, and at the site we are having some operations, we are lifting stuff up and excavating and drilling and sawing and things like this. And all these are causing some emissions, but these are rather marginal in comparison to those that were caused when the materials were initially produced. Then we have our building ready, and the building, when it's ready, it's consuming electricity or district heat or district cool, and it has to be equipped with different sort of materials, and the materials need to be maintained and occasionally replaced for a number of decades. So these all things are causing then long-lasting environmental impacts. Then one day, at least in a bookkeeping sense, the building comes to the end of its life cycle, and it's going to be torn down in an organized or unorganized manner. And of course, the energy that's consumed in this action is causing emissions, and then hopefully we could recycle or reuse some of the ingredients of the building. But unfortunately, there is, to this date, we don't have buildings that will be 100% reusable or recyclable, because the other ancillary materials than, for instance, your nice log frame might contain harmful substances that are prohibited from reuse and recycling, so you just can't reuse them, so they have to be landfilled. Anyway, this is the simplified life cycle of a building. And the good thing is that with this sort of calculation, which is, by the way, internationally standardized and has been there for a couple of decades already, you can estimate not only environmental impacts such as climate change or acidification or eutrophication, but you can also look at some social impacts or economic impacts, all with the same tool. So this is the benefit of life cycle approach. And for manufacturers, this also could reveal that where in your process you have things that you could tweak, where that you could improve, and hence lose less money and be more profitable. So LCA is also a tool for improving the performance of your company. So this might sound like it's a lot of hustle, but luckily we have nowadays digital tools that are used in the design of buildings, and when these tools are plugged in to those tools that are doing the LCA calculations, the sort of like manual or human labor is reduced. So we can pretty much rely on the help of machines in the future in this regard. Now let's have an example. How do these results then look like? What sort of like stuff do we get out of these calculations? And I'm going to use an example in Finland. Unfortunately, I couldn't find any results from a block building, but I will use a massive wooden building which is built in central Finland, in Jyväskylä. This is 8 stories high, cross-laminated timber building. It has one concrete cellar or basement floor underneath, and it has actually won the Architectural Finlandia Prize 10 years ago. So, with LCA, you can first of all get an understanding that how much does your building weigh? What are the heaviest parts of the building? Here we can see that actually in an 8-story high building, it's actually the stuff that you put under the building and around the building on the side that are the heaviest. So things that go into site and groundworks and foundations. Then we can also see that which individual materials are heaviest. It's actually rather revealing that in a fully wooden building, it's concrete and soil and asphalt that are so much more heavier than the weight of the wood. Of course, that's due to the lightness of wood, but also it opens our eyes to the metabolism of a building project over its life cycle. Then we can also see that how much of the materials are from recycled origin, how much of the weight of the building is from renewable materials or non-renewable materials. And again, in a fully wooden building, we can see that it's rather surprising that not so much of the weight of the building, even in a massive wood building, comes from renewable sources. Then ultimately we can also calculate the carbon footprint or CO2 equivalents and see the share, how much comes from the production of materials, how much comes from the use of energy, from the repairs and from the end-of-life operations. All this comes from the same sort of like assessment done with the digital tools. And then ultimately we can look at the different building parts and analyze their contribution to the carbon footprint. We can see that which parts are the most environmentally harmful, or in other words, where we should put our attention to if we wanted to reduce the greenhouse gas emissions of this particular building. But we can also look at the bright side, the flip side of the coin, and see that in which parts of the building we have the largest storages of carbon that are away from the atmosphere, away from causing global warming. So this sort of information you can get from your building with a rather simple and not that time-consuming process of life cycle assessment. I admit that I'm really trying to market it because I believe that this is maybe the only tool that can really help the building sector in the rehabilitation from its dependency and addiction to overuse of materials and energy. So this is the rehab process for building sector. All right, but back to the interesting topic that even in fully wooden buildings, actually we have so much more other stuff than wood. And even if we are trying to do good, we have somehow the idea that I want to do good for the environment or for the socio-economy or in Rapina or somewhere else by accelerating the use of wood in construction, but actually while doing so we are accelerating the use of other materials to greater extent than we are accelerating the use of wood, just because that there is so much other stuff that is used in the making of a building. Now, this doesn't necessarily apply to a fully wooden handicrafted log home in Estonia. This applies to the building I just showed, but maybe gives you an understanding that there is no like monomaterial building. Buildings nowadays are rather complex animals. Interestingly, when we look at the materials in European building sector, wood is less than 1%. So there is so much more share for increasing the amount of wood, but as we do so, we are also increasing the consumption of other materials as just described. Concrete however you measure that, is the leading material. And as we are shifting towards circular economy, in which we would reuse and recycle materials that already have been put to the built environment, it seems inevitable that concrete will maintain its position if we were to go into such a circular economy. However, when we need to have new materials poured into the metabolism of the built environment, then of course we should really consider that are we going to use non-renewable or renewable materials, and the latter of course is my preference. Let's go back to the global scale. So now we are past the complicated side of LCA, and let's talk about global consumption of construction materials. Here we can see that actually nowadays the consumption of materials for buildings is growing at a faster rate than the global population. And this, again, if we refer back to the early slides that I showed, that how small the remaining carbon budget is in comparison to the immense amount of emissions that are caused from building materials. This is something that there is no way of going around it. It's rather dramatic and rather worrying as well. Something should be done about this if we want to contain global warming at least below 2 degrees. With the increase of construction materials, we are also increasing emissions, and here we can see the projections in the emissions that rise from different materials. Concrete, steel, bricks and aluminum are leaving the pack and causing pretty much emissions over mid-century. And this, of course, as described in the beginning of the lecture, will cause sea levels to rise as a reaction to global warming. These are all projections made by UN, and we actually don't know how much the sea levels will be rising and how fast this is going to happen, because we really do not have any observations since the last time that this happened over 10,000 years ago. We don't have scientific documentation from those days, even though our ancestors witnessed that. But I was 2 years ago, I was speaking to maybe the leading climate scientist of our time, Professor John Schellhuber from Potsdam Institute of Climate Impact Research, and he said that in his view there is nothing that we can do to 2-meter sea level rise. There are only two questions. First of all, that how fast is it going to happen, and how much beyond 2 meters we are going to go. And now there are rather well-prepared documents saying that maybe we can't do anything about the loss of Greenland's ice sheets. I hope that these reports are wrong, but if they were not wrong, then the sea level rise that comes from the melting of Greenland is in the range of 6 to 7 meters. Again, the time frame is a question, but for the first time after the last ice age, we have entered a new era in which sea levels are not more stable. And interestingly, sea level stabilization some 8,000 or 7,000 years ago was the one fact that led into the birth of urban civilizations across the globe, when the rivers found their roots and when sea level stabilized. So it's going to be an interesting future to see that what is going to be the next cultural evolution after we are entering the unstable sea level era. In my country, in Finland, we have started to model that how would this look if we got 2 meters of extra sea levels. This is from the capital of Finland, from Helsinki. We are modeling that where would on the dashed line you can see the current sea level, and in the illustration you can see the 2-meter addition. Of course, much earlier that there would be water on the streets, the value of the properties would have collapsed. And as we have 80% of our national wealth in the built environment, this would of course be economically rather disastrous. And therefore, I'm really arguing that what we would need to do in the timeline of mitigating emissions in the built environment is that we should actively and rapidly need to start removing carbon from the atmosphere. And this is actually something that the IPCC also says. They are stating that the deployment of carbon dioxide removals to counterbalance hard-to-abate residual emissions is unavoidable. In other words, it means that even if your cement factory or steel factory would run with zero carbon energy, clean energy, there are chemical process-related emissions that you can't get away by using clean energy. And that's why you need to develop technologies that are absorbing CO2 from the atmosphere. How much? Let's see. And how much could be the potential of wood construction in relation to these. So there in the black bars over there you can see the typical possibilities of taking CO2 from the atmosphere, and the green bars depict like new ways of taking CO2 from the atmosphere with direct air capture and so forth. And towards 2070 we are in the range of 8 gigatons. Okay. Now, we don't need to remember these by heart, but if we just compare these to some of the scenarios that are there for increasing wood construction and the potential of wood construction globally to capture CO2, we can see that it holds the potential several times over to store the carbon that the IPCC says that should be stored away from the atmosphere. Of course, we cannot utilize this full potential because there are several conflicting land use change related issues and many other things. But the theoretical potential for wood construction is really great. Technically, it's very simple to check that how much carbon is captured in these wooden building products. We just need to know the amount of products. Then we multiply that with the product-related amount of atmospheric or technically captured carbon, and hence we get the amount of carbon in the product in kilos of carbon. And if we wanted to know the corresponding figure in carbon dioxide, we would just multiply this with 3.67 and get the figure for CO2 due to the different molecular weights of atoms of carbon and oxygen. So it's technically easy to assess that what is the carbon storage potential, and as you probably all know, roughly half of the dry weight of wood is atmospheric carbon. It actually varies depending on the part of the tree, from 40-something to close to 60-something, and it's different in different organic materials. Bamboo and hemp seem to be performing also extremely well, that they are close to 60%. But roughly you can say that in organic building materials, rule of thumb is that half of the dry weight of that organic material is atmospheric carbon. Yes, so we should utilize these sort of materials, and we should make them long-lasting in our buildings so that the carbon will be away from the atmosphere for as long as possible. But that's not all. I think that we shouldn't just think that the wood sector is gonna thrive in the future because of its unique capacity of storing carbon into the buildings and building products. Also, other sectors and other material producers aren't sleeping. They are actively developing their products and processes towards carbon storage. And me and my colleagues from Germany actually had a review of what are all the known ways of storing carbon into the built environment. And we looked at all that has been published in scientific literature for the past decade. And here's what we found. Of course, self-evidently, we have the bio-based materials, such as logs or new composites, such as mycelium-based materials, or anything even made from potato peels. So there is a broad array of different bio-based materials. But then in the building sector, in the built environment, we shouldn't forget the photosynthesis in plants. And this seems to be also quite good way to curb emissions. In our capital, in Helsinki, around 9% of the annual emissions of the entire city are neutralized just by the park trees and lawns of the city. So it's also related to what sort of city plans we are making. Then in soils, in urban soils, we seem to also have a good potential for storing carbon into the organic matter in the soils. And if we used certain minerals in a wise manner and mixed that with the growing medium, that the minerals, through their weathering, would also accelerate the accumulation of carbon into soils under our feet. And this is something that we don't have to actively interfere with at all. Then we have the age-old method of using biochar. And as we all recall, biochar is basically wood or any organic material that's burned in non-oxygen conditions, in a pyrolysis, and then we get biochar out of that. And we can add biochar into soils to make them more fertile. This has been used for thousands of years. But we can also add biochar into asphalt or concrete, and hence create very, very long-lasting carbon storages. Then we also have the combination of cement-based products, and this is what the cement industry or concrete industry nowadays is so actively looking at. But how could they intentionally accelerate the use of carbonation as a chemical reaction? Of course, as known, this also causes the rebars in steel to corrode, and that's the reason why you normally want to prevent it from happening. But you can intentionally let it happen in certain applications. Then if we go towards more like science fiction, we have possibilities for capturing CO2 directly from the atmosphere. There are pilot plants already running on this. It's very pricey at the moment, but hopefully the prices are going to go down. And then we have around 7 projects globally that are piloting with artificial photosynthesis. So they are making these so-called photobioreactors, sort of like solar panel looking things that have algae or some other organic stuff inside that's eating sunlight and growing biomass. These are not very successful. But let's imagine that we could make artificial photosynthesis work and we could capture CO2 directly from the atmosphere. If we could take that CO2, we could basically cook plastics from it and use those in frost insulations or sewage pipes and have long-lasting storages. And also something that's more of a dream of most of the construction sector nowadays is that if we could remove carbon from the atmosphere and inject that into concrete while it's curing, this would create a magnificent, from human perspective, eternal carbon sink. And this would be a tremendous business opportunity for those who want to invest or buy climate compensations. So as we can see, there are lots of different ways of storing carbon into the built environment, but which of these make sense nowadays? Which of these are mature enough that they could be taken into account? So this is how it looks when you put them into the order of maturity and applicability. On the top right corner, you can see approaches that are most mature and that hold the greatest potential for storing carbon. And on the bottom left corner, you see applications that aren't so. So we can see that no-brainer, we should, use as much bio-based materials in construction as we possibly can nowadays, because that's an existing technology that doesn't have to be developed in a lab. But then also biochar is something that around the building should be actively used, because it's not only gives you carbon storage, but the production of biochar also gives you energy. So you can tap that into your district heating system, the making of biochar. And then we have the plants and CO2-cured concrete and a combination of cement-based products, which are sort of like runner-ups that are coming there, and there is lots of investment interest in these things. So maybe my message here is that even though wooden products are very climate-friendly, we shouldn't just, take it assured that this is going to be there forever. We should also try to improve and think of new ways of how to promote this. So in all, I think that in the building sector we should try to mimic what the nature is already doing. How to learn from the nice carbon balance that is out there in forest or in nature. Plants are breathing carbon in and out, and when they are storing carbon into their biomass and when they are decomposing, the carbon is released back to the circle again. Is there a way of mimicking this in the built environment? Yes, there are some possibilities for that, and now we are getting towards the boring part of my presentation. If you thought that the previous was that, you were unfortunately wrong. So I'm going to talk about what's there in the policy pipeline. So many countries at the moment in the European Union are looking for setting emission limits for buildings, and some countries, such as Finland, have also set incentives for storing carbon into the built environment. So these would be the ways, from the policy perspective, of how we could, do something about to mimic the natural carbon flows in the built environment. These all are related to something that's called Fit for 55. It's not a training program for us middle-agers, but it's a package of European climate laws, and there are 3 interesting policy packages that maybe we should be aware of, because it has to do with what we are, manufacturing or trying to sell or trying to design. First one of these is the taxonomy for sustainable activities. In short, it means that if somebody wants to invest her or his extra $10 million into something that does good for the climate, the EU has set a rule criteria that have to be fulfilled so that the investment can with good conscience say that yes, it was a green investment, so that because otherwise every factory could go saying that, hey, yes, our process is so clean, please invest here. But there are technical criteria, and some of these criteria are also for buildings and infrastructure projects. And it already is now written into this regulation that if you want to have green investment to your building, you need to have so-called climate declaration, or basically means carbon footprint calculation. And there are requirements for recycled contents on the building. And in wooden buildings, there's actually rather strict. It's 20% of the weight of the frame has to be reused or recycled, and this is something that will be a challenge for the wood sector. On the other hand, logs are so easy to reuse, so my suggestion to the log sector would be that you guys should actively start looking at ways of how to add a few reused logs into your frames to comply with these. Then the next thing that's in the pipeline is the revision of EU's Energy Performance of Buildings Directive. It's a mouthful, but in short, it's the one package that is steering and governing the energy use in buildings. And the new addition to this directive, which I welcome warm-heartedly, is that it's going to set a mandatory carbon footprint calculation requirement from year 28 onwards. And the great thing is that it's also going to set the possibility for calculating and reporting the carbon that's stored into the buildings as well. And the third thing that we should all be aware of is EU's construction products regulation. Now, there cannot be any national regulation that's relating to construction products in any EU member states. There is one regulation that fits all countries' needs, and it is the CPR. And in this new CPR, there is a new mandatory requirement that products have to declare. Every construction product that falls within the scope of the CPR has to come with carbon footprint information. You just can't hide that anymore. And secondly, you also can report carbon that's stored into your product. So I think that these are very positive changes in policies. And now let's have a look about the Energy Performance of Buildings Directive and put that into timeline, because this is coming very rapidly. Next year, there's going to be something that's called Delegated Act for the calculation of life cycle carbon footprint. In practice, this means that the EU's Commission is going to set same rules for everybody who wants to calculate the carbon footprint. So there can't be any great deviations on, like, this country is going to calculate this way or that country is in another way. It's going to be more or less harmonized. In 27, so 3 years from now, all member states have to give reports to the Commission that how are we going to start reducing emissions in our national building stock. And if I were working in the wood sector, this would be now my window of opportunity for lobbying to the policymakers that what is going to be the role of wood in this quest. Then from year 28 onwards, the carbon footprint calculations will be mandatory for buildings that are over 1,000 square meters large, and from 2030 for all new buildings. And latest that year, the countries have to implement their plans to limit the carbon footprint from the building stock. So this is something that maybe some of you might find relevant for your collaboration and discussions with politicians. So, in short, I'd like to summarize by saying that, first of all, the increasing construction needs are unfortunately a serious and very, very challenging risk to climate change mitigation efforts. And therefore, new buildings must have very small carbon footprints while trying to maximize the potential of carbon storage in the buildings. And thirdly, I would say that we, the construction sector, we will have a historical role but also responsibility in building well-being for the growing global population, but within the planetary boundaries and not by exceeding them. And this is something that we just can't turn our back to. I think that it would be intellectually lazy not to face this fact. On the other hand, this puts us in a position that we are one of the few sectors that can really have a great and important significance to this. And let me just finalize with something that I consider to be a little bit more poetic. We've been talking about carbon. Over there, it's the fourth abundant material in the universe by mass. But why are we so interested in this, and where is it actually coming from? It didn't originate actually in the Big Bang. Carbon actually comes from the cores of ancient stars that exploded billions of years ago, because when stars are forming from hydrogen, and when hydrogen starts the fusion project into helium, towards the end of the life of a star, the pressure gets so immense that the atomic nucleus are forced together, and heavier materials such as carbon are formed. And then when the star dies, it sort of like explodes and blows some of that stuff into our cosmos. And from that dust, our solar system was formed. So the thing that we have, half of the dry weight of wood here, was made billions of years ago, somewhere very distant part of the universe, at the hearts of ancient stars. And now we are using it here on our planet, hopefully for a long time. But ultimately, in 500 million or 1 billion year or so, our star will also run out of its fuel. And when it does so, it's going to grow into a red giant, and it's going to either melt Earth or blow Earth's ingredients into this space. And then these heavier atoms, such as carbon, will continue to float in the universe and maybe someday form another constellations. So this sort of like a universal perspective to all construction is somehow poetic. We are operating with eternal materials from our perspective. We are using them for a tiny bit of time for making nice buildings. But maybe this helps us to love the log even more by understanding its universal and ancient origin, and maybe this also helps us to make sure that we are not letting the carbon to escape into the atmosphere too fast, but that we are keeping the carbon in the log and reusing the logs many times over, because after all it's billions of years old product from ancient stars. I think that I have now used enough of your time and attention, and I hope that there was something that you could utilize in your career. And if there's interest to discuss these things later on or learn more about LCA, you can contact either me or Annika. There is an online course coming on this in English, which is available globally. So those of you who are interested in that, so just get in touch with us. Thank you for your attention.
That was very interesting and something that we have to think about in our future. Our next speaker is Janis Soderstrom. He'll be talking about sustainability. He's with ABB. He's one of our gold sponsors, so it's very important. ABB is a technology leader in electrification and automation, enabling a more sustainable and resource-efficient future. The company's solutions connect engineering, know-how, and software to optimize how things are manufactured, moved, powered, and operated. Getting worried.
Thanks. All good. happy to be here. Thank you very much for the invitation. It's actually a small advantage to have the presentation after Matti, because he was talking about the same things that I was going to say. So I'll be more short and brief than I was first expecting to. Small introduction. My name is Jonas Söderström. I'm business developer for Nordics, Baltics and UK for ABB electrification smart building. I will tell you a little bit about the sustainability and the work that is happening inside ABB, why we are doing it, and what implication it has. It has some for you also, because it shows what the market is asking for. And let's start it off. So, why are we engaging in sustainability? This was covered in the last presentation. Of course, we have a lot of these environmental issues. We have aging population, drought, wildfires, pollutions, etc. And building stands for more than 30% of energy-related emissions globally. So let's take care of it. It's built up like this. So first, market insights. We will look at ABB's sustainability goals, our climate ambition, how we do it, resources, sustainability is the way, and some product examples also from ABB. So, the megatrends that are shaping our world is seen here. We are talking about energy transformation, going from fossil to circular, digitalization, connectivity, urbanization, and also a shift to electricity. This is what we see today. And tying these all into sustainability will make some advantages for us. So, the sustainability goals of ABB is to achieve carbon neutrality by 2030. And we have three pillars here. We enable a low-carbon society, we preserve resources, and we promote social progress. Not going into all the details here as such, small text and all. But here you see how the transformation has been developing. Now, of course, in the beginning, you see that there are fast wins that you can do. But then, coming from now onwards, it's going to be heavy work in doing changes in operation, changing in materials, etc. Because you cannot achieve this with only going one way. We have to work at several areas. We are talking about, if you are familiar, we are talking about the greenhouse gas emissions, scope 1, scope 2, scope 3. And that can be a challenge sometimes, but you will encounter these terms, this terminology. When you're selling to the market, they will be asking you to give environmental product declaration, which is actually a document conforming a little bit with what this LCA is. These are some examples of ABB's strengthening and accelerating of the sustainability agenda. So consistently working throughout the business with these development tracks. So, own operations, as we heard in the previous presentation by Matti also. Scope 1, Scope 2, product circularity, carbon neutrality. Then suppliers, and then customers. These are all the pillars that you will be working and encountering if you go into this. And here we see some of our achievements and targets. So, scope 1 and 2 emissions, greenhouse gas emissions limited versus 2019 baseline. By 23, we have achieved 75%. This year we will reach 78. We are doing this by decarbonizing and electrifying, and also making the operations carbon neutral. Now, there is a lot of talk about how to compensate. I want to compensate something and do something, but this has taken a small how to say, murky tone, because people are talking about greenwashing also. So I plant 100 trees in Latvia, and by doing so, I feel that okay, I have compensated now, because now I'm allowed to use harmful materials or so in my calculations. This is not the way to go. You should concentrate on your own operations. If we do good and plant trees, excellent, but don't keep it separate from these goals that you make for your own health. So, how did we do it? You need to map these things. You need to be a science-based approach when you look at it. So we have upstream, looking at the supply chain and reduce the emissions you get from there. You have to reduce carbon in your own operations and support customers then in reducing the annual CO2 emissions. These are the main streams that we are working with. It's not moving. Oh, it did. It was a little bit too fast, sorry. Have to wait until the slides catch up, but okay, let's see. Okay, so we have one team that is Mission to Zero. That is our own operations, and here our idea is to achieve carbon neutrality within our own production facilities, as we are doing. I'm giving you a few examples of these. So far, we have 11 sites where we have done this, implemented this program. And the one closest here is actually in Porvoo, Finland. And this is the factory. So, how did we achieve it? Through geothermal system introduction, energy recycling from production, and a solar power plant. So total energy efficiency increased by 21%, and CO2 emissions decreased by over 600 tons. Not bad, but we did more. We also see that as the resources are limited that we are operating within our world, then we need to engage in circularity, as we saw also here earlier presentation. And circularity can be a lot when you are dealing with electricity. You have to take into account safety and norms connected with that. So you cannot get away from reducing all the plastics in the world in that sense. You still have to use it today. But you can recycle, and you can also use other materials. For example, I'm going to show you here some of the materials. So product examples. Recycled plastics, and also biocircular plastics. Biocircular is a plastic that has never been fossil oil. It's tar oil, pine oil, for example, that's been used to do these plasticides, or recycled plastics that we then use again. And by using these recycled plastics, etc., we are today, here are a few examples covering about 42 tons. And today we are over 150 tons. And it's increasing, it's increasing. Other examples is how much water you save. One plastic box made of recycled material instead of virgin material results in 90 liters less water used. That's a lot. So you can basically have a swimming pool that you have, like inside your apartment, just with small boxes. All right, yes, more of these product examples. One thing that you will probably see when you are, or if not already, is EPDs, environmental product declarations. That is something that your customers will ask from. What is an EPD? It's actually a standardized format of the LCM that Matti was talking about earlier. There are several of those, but here are also what we talked about earlier, sustainability throughout the product life cycle. Look at the design, use sustainable materials, look at your production, product data, use phase, and end of sales. I feel like I'm a little bit repeating what Matti talked about here in the last presentations. This is how big companies see the playing around what we are talking about. And also the customers are asking for this. Do you have EPDs? What is your approach to sustainability? All of this. Short and sweet. I promised to keep it a little bit shorter than planned, because we had a good presentation from Matti here earlier. So, any questions now? Happy to hear them afterwards also. Thank you very much.